Welcome to Chapter 3 of the Shapley Values series. In this chapter, we want to discuss what explainability models are and which desirable properties they possess. Let's dive right in. So we now know that we would like to have an explainability model that can wrap around any machine learning model. Ideally, as an outcome of this procedure, we want our forecast to be explainable in a simple additive fashion, just like it is possible with a linear regression model. As we know, here we attribute different influences to the forecast by simply multiplying the influences with the input data and then adding them up. The sum of these influences then equals to the prediction value. Since we expect exactly this behavior for our explainability model, we will refer to it as an additive feature attribution model. An additive feature attribution model can formally be described as such. Don't panic. We will walk through this step by step, and you will see that it's actually pretty simple. Let's assume that the prediction made by our machine learning model can be expressed as f of x. X is simply our data input, that is, prices and so on. And f is simply our machine learning model that produces the prediction for a given input of data x. This makes sense because a specific prediction is made by the machine learning model based on the specific data input for that prediction. So what is G? G is the output of the explainability model. In contrast to the machine learning model, the explainability model doesn't use the actual data x as an input, but instead uses z prime as an input. Z prime is just the whole set of features, which in our example corresponds to the price feature, event feature, and so on. So for example, instead of giving the explainability model the specific price value of, for example, 2 euros, we just tell the explainability model that that specific price should be considered as a feature, that is 1 or 0, or true or false. The prediction is then just distributed over the influences of all the features z prime. We expect the output of the explainability model G to be very close to the output of the machine learning model F. But why do we need an explainability model that simply produces the same output as the machine learning model? The answer is the way that the explainability model explains how the data input contributes to the prediction output. The feature influences of the machine learning model F can be arbitrarily complex, but the influences of the same features in the explainability model G are always just the sum of all the features effects, for example price, temperature, and so on, where M represents all features. Z prime sub I here only represents a binary flag, that is 0 or 1, that says whether the feature value z prime sub I is part of the explainability model. So for example, the feature I could be price. If I equals to price is part of the model, we will set z prime sub I to 1, and if price is not part of the model, we will set z prime sub I to 0. Phi sub I is the weight of the individual feature in the sum. This weight is exactly what the explainability model uses to express how much the respective feature contributes to the individual prediction. Lastly, there is phi sub 0, which can simply be interpreted as the mean prediction if there were no features in the model. We will later see how the values for phi sub I and phi sub 0 are calculated. But note for now that they are the key components that tell us how much a feature contributes to the individual prediction, no matter how complex the underlying machine learning model is. The main takeaway is that we are now at a state where no matter how complex the machine learning model's feature correlations are, the explainability model can represent those influences in an easily interpretable and additive form. In simple terms, the explainability model is able to express the feature effects even for a complex model like a deep neural network in the simple form of an additive feature attribution model that looks a lot like a linear regression model. Remember, we didn't change the underlying model that creates the prediction, but simply developed an explainability model on top of the machine learning model that expresses the effects of the machine learning model's features in an interpretable way.